Okay, so in the first place, let me extend my heartfelt thanks to Chung, to Ben, and the entire team of organizers for their very excellent organization of this wonderful conference, and for all the distinguished participants. And I'm grateful to the organizers for giving me this opportunity to be able to talk to you and to present a few points that I have in my mind. So as the title suggests, I'm going to talk on the LightFront quantization of the Fermionic Schwinger model. I have added the word fermionic on purpose. It's a Schwinger model. It's going to be, eventually I'm going to talk about the vector Schwinger model, but fermionic in the sense that I would be dealing with the Fermi fields. So let me tell you in 1 or 2 minutes that prior to the last 2 years, I myself was not using directly the Fermi fields for the LightFront quantization. And now I could dare to do this in the last 2 years because of the great pioneering work by Philip Mannheim, Peter Loden, and Sten Brodsky, which they call as the formulation of so-called good fermions and bad fermions. And that makes it possible to directly deal with the LightFront quantization of the fermionic fields, whichever theory. So, for example, last year I presented some calculation on a supersymmetric field theory given by the Best-Juveno model, where apart from scalar and pseudoscalar fields, there were some vector fields. Oh, there were some spinor fields, fermionic fields. And I was able to make use of this formulation of so-called good and bad fermions due to Mannheim, Loden, and Sten Brodsky. And I'm again going to, this is just the second calculation that I have taken up. This is in the context of a two-dimensional model, which is very popularly known as Schwinger model, which is, in fact, I'm going to talk about today, the vector Schwinger model. So here you see the action is defined in terms of some Lagrangian density, which is a function of some spinor field psi bar, and the vector field A mu. So this is just the kinetic energy of the vector field, U1 gauge field. And this is the famous Dirac Lagrangian. So nothing special about it, but I'm going to write it in only in 2 dimensions. And this term and this term, these 2 terms, they obviously represent some interaction terms. As you can see, a product of psi bar, psi and A mu, psi bar, psi and A mu. And here is the coupling coefficient EL and ER. So if you set EL equal to ER, then this would be the vector Schwinger model. And if you set EL not equal to ER, whatever they are, but if they are unequal to each other, then that belongs to the case of so-called chiral Schwinger model or chiral theories. So here, when I set ER equal to EL, which describes the coupling of the right-handed and left-handed fermions with the vector field A mu, then the terms involving rho 3, which is analogous to gamma 5 of the usual Dirac matrices, they would drop out, and what we are left with is just these three terms. So the kinetic energy of the vector field, the Dirac spinor, the Dirac Lagrangian, and the interaction Lagrangian. So here I have set EL equal to ER equal to E. So that is all about this, and psi bar and psi dagger are the usual Dirac conjugate and Dirac adjoint. And so psi bar and psi dagger, the Dirac conjugate and Dirac adjoint, they are related through the matrix rho 0. And depending on one's choice of notations and conventions, you get this vector of iota here, or somebody includes it there. So anyway, I'm going to follow the conventions of the string theory by Baker and Schwarz. in string theory or in supersymmetry or supergravity theory, you invariably have to have Fermi fields, and therefore I'm trying to stick to these notations of Baker and Schwarz. So here ρ0 and ρ1 are given by these two definitions, and psi bar and psi dagger are related to this. These two are equivalent expressions you can. And these Dirac matrices rho mu, they must satisfy the Dirac algebra. So this is rho nu is minus twice eta mu. So it depends on the choice of your metric tensor. If it's +1 -1, then I'm going to have minus here. If I have -1 +1, then I have to have a +1 here. So that's a minor thing, but we keep in mind. And ρ3 is our usual matrix analogous to gamma 5. So chirality for a Dirac fermion psi is defined through the operator ρ3, which has eigenvalues ±1. And we also notice here that ρ0 square is -1 and ρ1 square is +1, so that the inverse of ρ0 and ρ1 exists. This is this is going to be very crucial. And the formulation of Mannheim, Loden, and Brodsky is based precisely catching this particular point, that when we handle the same theory in LightFront quantization, then we end up in some new matrices, which is rho plus plus minus ρ1, which would be rho plus minus, and their inverse does not exist because their squares are going to be 0. I will come to it in a few minutes later, but this is the main catching point of the this great piece of work by Mannheim, Loden, and Brodsky, and I'm going to make use of it in a very specific manner in my own calculation. So after having described the so-called vector Schwinger model, let me now construct this model from the ab initio, as my friend James Very would like to call it, from the fundamental principles. So I start with the Dirac Lagrangian, and this I can check that this has a global gauge symmetry or the global symmetry. And I would instead like to make an interacting QED theory. And for that purpose, I would like this to have local symmetry. And there is a standard procedure for doing it. It's called as the Neuders procedure. So what do I do in this is I first replace my partial derivative del mu with the covariant derivative capital D mu, and I introduce a vector gauge field A mu here. Then this vector gauge field A mu would not be dynamical unless I introduce a kinetic energy term for this field. So what I do, in order to make this field A mu as dynamical, I add the kinetic energy term for this field given by the famous Maxwell Lagrangian in my Dirac Lagrangian, and then I just expand this capital D mu, which gives rise to these two terms to me. And so I am back with this Dirac Lagrangian, and this is the additional interaction term. And you can check with my first two slides that this Lagrangian density is identically the same that I started with for the vector Schwinger model. And now we can start with with studying this model, analyzing this model. Very good. After we have understood the main concepts involved, now things are going to be easy. Let me break it up into two parts: the bosonic part of the Lagrangian, and this is going to be the fermionic part, this plus this, where this is going to be Dirac Lagrangian and this is going to be the interaction Lagrangian with the coupling coefficient E, which is the same for the left-handed and right-handed fermions, and they are coupled with A mu with the same coupling. So standard QED coupling psi bar A/psi. Okay, very good. Now this, you see, this is bosonic piece, and these two together constitute the fermionic piece. So the first piece is the Dirac Lagrangian and the second piece is the interaction Lagrangian. Now one more step, that I can write the Dirac Lagrangian in two different alternative methods, and I would be simultaneously considering the analysis for both of them. So this is, I'm calling it L1, and this is L2. And you can very easily check that the difference of these two is just a total derivative. So when I put it back in my action and I integrate it over all time, this term would disappear. It will not make any contribution. So I'm convinced right from the beginning of my theory that the physical contents of these two theories are just going to be identically the same. And we will see that algebraically they would look differently. In my calculation, I will point them out. And when it comes to the giving the physical result, they would yield identically the same physical results in both the cases. Very good. So having done that, we have very clearly, okay, so the Dirac Lagrangian plus interaction Lagrangian, I am calling it L1 with full Fermi Lagrangian. And in the second choice, L2, when added to interaction Lagrangian, gives me L2. All right. Now let us proceed with the Dirac's well-known procedure of the so-called Hamiltonian formulation and path integral formulations. Of course, I mean, also led by many more experts in this field. So this is the fermionic piece. I write it in the component form like that, and I can obtain the canonical movement as for the bosonic piece of the theory. But I see that pi0 vanishes, and when pi0 vanishes, but pi1 does not vanish. So this pi0 gives rise to me a Dirac primary constant. I call it chi1 pi0 equal to 0. And then I go on to calculate the fermionic momenta. We have to watch out that these fields involved, they are fermionic. This is the time derivative with respect to psi of this. So this is del mu here. So this involves a del 0 psi. So I can differentiate it there, but I must take this entire operator to the right hand side of psi bar, which, and in the process I will pick up a minus sign. Very good. Or you use the definitions of the directional derivatives, you arrive at the same result in both the methods. However, pi bar comes out to be 0. So what is this? What does it tell me physics wise? It tells me that the field psi and psi dagger, or psi and psi bar, are to be treated as independent fields. One cannot be obtained from the other. And the same holds for pi and pi bar, or pi and pi dagger. One cannot be obtained from the other. So they are independent fields. Okay. And here, as the right-hand side does not involve any velocity here, so this gives rise to me a Dirac primary constant here and another Dirac primary constant here. So I have altogether 3 Dirac primary constant, and the bosonic part can be, I mean, all these constraints I would eventually ask them to hold true for all time, and therefore that would determine if I have secondary constraints or not. From bosonic part, I find that yes, there is indeed the Gauss's Gauss's law of divergence follows from here, but for omega 1, omega 2, for the fermionic constant, there is no such thing. And here I would just point out that this we must notice that this rho 0 is sitting here. Okay, in one of them, it's not there, in the other, doesn't matter. And I have to do the same calculation with the second version of my Lagrangian density. And here I find the result to be minus 1/2 psi dagger, pi equal to minus 1/2 psi dagger. And pi bar is given by this, which would mean pi dagger equal to minus 1/2 psi. So pi is minus 1/2 psi dagger, pi dagger is minus 1/2 times psi. And these two would lead to these 2 Dirac primary constants involving rho 0 matrices and psi bar here and pi bar here and rho 0 matrix. Okay, I can write them in terms of Dirac adjoints, psi dagger and pi dagger. So these 2 constants could be written like this. And then let me set out the conventions for the Poisson brackets of the bosonic variables and for the fermionic variables. You will see The fundamental Poisson brackets here are the same that we have in bosonic theory, but here there is a, this is also plus, this is also plus, but here it was plus and minus, okay? So we have to watch out. Now we construct the canonical Hamiltonian using the standard Legendre transformation. Going step by step, we finally end up with this result. And if I add up my three primary constraints with the help of Lagrange multiplier fields, U, V, and W, then this is going to give me the total Hamiltonian. And let me emphasize that total Hamiltonian, if we write down the Hamilton's equations from total Hamiltonian density, those Hamilton's equations are going to preserve my constraints of the theory for all time to come, okay, for all time. And so it is, HT is very important. And moreover, also, you also construct the first order Lagrangian density of the theory, making use of this total Hamiltonian density. And first order Lagrangian density goes to define my path integral, which I will show at the end of my slides. Now, so I just summarized the results so far. This one primary constraint, one secondary constraint, these two primary fermionic constraints in one formalism, with another version of the fermionic Lagrangian. These are the four constraints. And now you realize that you obtain the matrix of the Poisson brackets of these four, and that is going to be identically the same. So this delta is the shorthand notation for delta of x1 minus y1, the space variables of this two vector x. All right. And this is very visible to us that the first row is 0, first column is 0. So it's going to be a singular matrix, and the constraints are going to form a set of first class constraints. Fine. I go over to these two gauge fixing conditions, time axial gauge, and Coulomb gauge. And I obtain, under these gauge fixing conditions, I again obtain the matrix of the Poisson bracket. And again, under both of them separately, you try to obtain, you will end up with the same result. Okay. So this is the partial derivative of delta with respect to the first variable x1. Okay. And then you can write down its determinant, and you can invert the matrix and everything. And then, so this matrix, as you see, is invertible. It's a non-singular matrix. And okay. So you can invert it. So this epsilon is the step function, usual step function, corresponding to the space derivative of this delta prime. This delta prime and epsilons, they are very, very highly singular distributions. And nevertheless, as long as we handle them correctly, no problems. And now, after a straightforward but rather lengthy calculation, you arrive at these results. So you see in these last three results, these are the equal time commutation relations, and the last three are the equal time anti-commutation relations and I obtain them using the standard Dirac procedure. And I need to remind that if I choose a different choice of gauge fixing conditions, then this result would not be the same. This would be different, and I have to work it out. But of course, using this gauge fixing condition and this gauge fixing condition gives rise to the identically the same result to me. So this is one thing, and I must emphasize here, when I'm now done with the instant form quantization of this theory, the choice of these gauge fixing conditions, as I have done in this particular case, is extremely important. They must make my matrix non-singular, which was originally singular. And we must not accept at any place, howsoever complicated or simple theory we are considering, we must conform with the Dirac's analysis, which happens to be one of the best papers on theoretical physics of the previous century. And I'm a great devotee of Dirac, so I like to advertise it. All right, now let us go over to the LightFront quantization of the same theory. So I again recap that my rho 0 square was minus 1, rho 1 is the unit matrix, so not a problem. And the inverse of rho 0 exists. Okay, that was the main point. But now for going to LightFront quantization, I construct gamma plus minus, which is rho 0 plus minus rho 1. And you see rho, by mistake I have written gamma, it should be rho. I'm sorry, this is rho plus minus, rho plus minus. So rho plus minus square is 0, and therefore the inverses of these matrices do not exist. And now I go to this formalism of so-called good and bad fermions due to my great friends Philip Mannheim, Peter Loden, and Stan Brodsky. And this formalism makes use of the so-called projection operators. In my theory, in my calculations, I make use of this lambda plus minus to be defined by minus 1/2 rho 0 times rho plus minus. Okay, and these are the very famous papers of Mannheim on these things, and PRD, and this select publication, and then this physical review. These two, well, this I think is a different paper. This talks about the different forms of dynamics. So this I have quoted here that, oh, this is the PRD paper. Good. So these three papers for me are very, very crucial. Otherwise, my calculation would collapse. So I go to the conventions x plus minus equal to this, and del plus minus equal to this. Now I again go to the bosonic and fermionic parts of my Lagrangian density, and I obtain the canonical momenta as I did before in the instant form quantization. So my pi plus turns out to be 0, and I remind that this pi plus is canonically conjugate to A minus upstairs, and pi minus upstairs is canonically conjugate to A plus upstairs. So this does not give me any constant because this is a velocity, time derivative of A plus, okay? So I have one Dirac primary constant once again, and I follow the standard Legendre transformation that to calculate my canonical Hamiltonian. And then now, if I need to do it now, I think I would need it later. So I would include bosonic and fermionic, both the parts in my theory. Now let me come back to the so-called projection operators that need to be constructed in this formalism of Mannheim, Loden, and Brodsky. So I do it like this, and one can verify the proper standard properties of the projection operator. So its square must be equal to the same thing. Its dagger adjoint must be equal to the same thing. The sum of the two projection operators, there are only two in this theory, comes out to be unit matrix, and the product of two is a null matrix. Fine. And rho plus minus here is my rho 0 plus minus rho 3, and its square is 0. Okay, so rho plus minus is not invertible. Okay, now with this, I redefine my fermionic fields. I call it zeta.
Just a quick note, Daya, we have 3 more minutes before we enter the 5-minute period set aside for questions.
Okay, thank you. So I construct the zeta and beta, my good and bad fermion fields, defined in terms of the projection operators. Very good. And I again obtain the canonical momenta. Here now it's minus 2 zeta dagger. But please notice that if I do not have this good and bad fermions zeta dagger, then I would have a rho plus here, and eventually I would need to invert that, and I will not be able to invert it. So that is the help of this formalism due to these friends. So these are two constants, and so this involves rho plus and these two. So now, and in the second L2, I have pi equal to minus zeta dagger and pi bar equal to this, which gives me these two constants, pi and pi, involving pi and pi bar. Both of them, they involve rho plus. But if I rewrite them in terms of the good fermions zeta dagger and zeta, then I would not have any problems whatsoever. I write down the canonical Hamiltonian of my theory constructed from Legendre transformation, and I write down total Hamiltonian. And let me skip this comment. So now in one case, these are the 4 constraints. In the second case, these are the 4 constraints, and I can calculate the matrix of the Poisson brackets properly. And this is a singular matrix, so I can choose, I must choose the gauge fixing conditions. And here I choose, this is the time axial gauge, A minus equals to 0, and space derivative of A plus equal to 0. And in both the cases, you will find that this matrix M alpha beta comes out to be identically the same in both the cases, whether I use this one or I use this second set of gauge fixing conditions. And this matrix is non-singular. I can invert it. I can write its determinant. So I need it for my path integral quantization of the theory. And now I have inverted the matrix, you see delta. And okay, so everything goes well. And now I can go over to the lengthy Dirac procedure, which is rather long. Usha might, if she has time, she might display the calculation of just one similar object in her calculation, which goes over to several, it involves several multiple convolution integrals to arrive at these results, in fact. So it's a very lengthy process. Here you just mention the results, no problem. And then I can come to the path integral quantization, because the stage is now set. We know everything about our theory in terms of Mr. Paul Maurice Dirac. So you can write the vacuum to vacuum transition amplitude for your theory, which is the transition amplitude from vacuum to vacuum. So what is one vacuum refers to the time t going to minus infinity, the first vacuum, and the second vacuum refers to, in the S matrix theory, the second vacuum refers to t going to plus infinity. So in fact, you are considering all summation over all of them. So t equal to minus infinity, vacuum at t equal to minus infinity, initial state, and final state vacuum defined at t equal to plus infinity. So wonderful. And here, as you will see, minus ht. This is, Mr. Dirac has given me this result. So essentially, I'm making use of the first order Lagrangian density. I could have written that instead of all these things. So never mind. And this here, this d mu is my phase space measure. So here, it is only given symbolically, but I write it down explicitly for in the two cases. So here, this comes from the square root of the determinant of that matrix, which I calculated, and all these constraints are there. So this is in the first case given by L1, and this is for the second case. So the constraints are different in the two cases. And then, so with my slides, I am essentially through, except that if James is kind enough to give me a couple of minutes to make some of my general remarks. So here, in the first place, let me complete the things on path integral quantization. These two expressions do look different, but if you write them down on the reduced hypersurface of the constraints of the theory, then they will yield identically the same result. So that is one thing. And that is just one remark about this. You can further proceed to calculate 2-point function, 4-point function, whatever you like. If you are interested in the so-called functional field theory, then this would be your starting point for doing the functional field theory. However, I have some 2 or 3 general remarks and suggestions to my entire LightFront community. This is in the nature of that in my entire calculation, I was keen on showing these results, and I wanted to highlight a few things. We all know that LightFront Hamiltonian is very crucial and must be done very correctly. But often I suspect I may be incorrect. I'm sorry for that. I apologize. So the choice of the gauge fixing conditions and the actually, I do not have any choice for imposing my equal time commutation or anti-commutation relations on my theory. Howsoever complicated is my theory, I must work it out to obtain correct equal time commutation and anti-commutation relations for my theory. Unless I do that, I should not simply assume that now, okay, now I impose this equal time commutation and anti-commutation relations on my theory. This is not acceptable to Mr. Paul Dirac. I'm sorry. And what the same also holds true about the gauge fixing conditions. You see, the gauge fixing conditions for any theory, they are arbitrary in some sense that this matrix of this Poisson brackets has to be eventually made from singular to non-singular. So but the choice must again be consistent with Mr. Paul Dirac, what he says, what he said in 1949, 1950 in his famous paper in Canadian Journal of Mathematics, one of the best papers on theoretical physics. We often do not care about it, or not many people really somehow are interested, or they try to ignore Mr. Dirac. That is not a very good thing for me. It annoys me also. I'm sure Mr. Dirac would be annoyed if you don't follow him. So we must follow him. So we must choose the gauge fixing conditions in such a manner, you see, so that these are the gauge fixing conditions. They must be consistent with this procedure. That matrix must be, I must be able to invert it. I must be able to write down a matrix which is invertible like this. I have shown these two explicit examples, one corresponding to the instant form quantization and one corresponding to the LightFront quantization. And if you look back at my last year's work or talk, then I did the similar thing with respect to the Bad-Fermion model, a supersymmetric field theory that involved Fermi fields. And I'm looking forward to many more future successful calculations, making use of the work by my three friends, Mannheim, Loden, and Stenbrodsky. And with that optimistic note, I can conclude my talk, James, for today.
Thank you very much. Thank you, Daya. Okay. Philip has had his hand up for a few minutes, and I'm sure he has something important to say. But please go ahead, Philip, but please keep it short. We're running a little short.
Well, first of all, Daya, thank you for your presentation. What I wanted to say is, despite all your kind words about my work with Stanley and Peter, we did not invent good or bad fermions. We only borrowed them from what was already in the literature. Our interest was,
but it came to my knowledge through your talks in the last 2 years.
Okay, thank you. I see. Our interest was.
I hope you will not be annoyed with my use of your formulation, and I hope I have done it correctly.
No, everything's fine. I'll just tell you what we were concerned about. While you have the good fermion anticommutator, we also constructed the good-bad and the bad-bad. And they look radically different from anything in instant time. But nonetheless, when we looked at the non-equal time, instant time anticommutator, we were able to recover all of the good, bad, and bad anti-fermion anticommutators. And the only reason they look so complicated is because you're restricting them to equal time, equal LightFront time.
Yes.
You're absolutely correct. When you want to do the path integral, you're not restricted to equal time. Correct. Therefore, you must use, the measure must contain both the good and the bad fermions. And that was one of the points that we stressed.
So Philip, I would like to assure you that I would carefully look into your other, and I would be in correspondence with you to locate your correct work that I would really like to learn further and put them to use in my further investigations.
Okay,
but I'm really enlightened to have your comments and to have you physically here, and you endorse that I'm not doing blunders, so that makes me happy.
So let's let that be the final word. Thank you very much, Daya, and for the extended discussions also with Philip. Now it's time to move over. If you would kindly turn off your screen sharing, Daya, we'll move over to the next and final talk of the session.